In this video, we're just going to talk about a few examples of diagonalization. The first example is this upper triangular matrix that we've encountered previously. We've seen that this matrix has distinct eigenvalues, lambda 1 equals 1, lambda 2 equals 2, and lambda 3 equals 3. Because the multiplicity of each eigenvalue is 1, E1 is the span of the vector 1, 0, 0. E2 is the span of the vector 1, 1, 0. And E3 is the span of the vector 3, 4, 2. We know that these three vectors will form a basis for R3. So we can form the diagonalization of A using the matrix P, which has entries 1, 0, 0, 1, 1, 0, and 3, 4, 2. The diagonalization D will take the eigenvalues for each of the columns in order along the diagonal. So this is important. The order does matter. The first eigenvalue, 1, goes with the first column of P. The eigenvalue 2 goes with the second column of P, and the eigenvalue 3 goes with the third column of P. We can use Sage to see that if we take P, D, P inverse, then we will get the matrix A. So this gives us our diagonalization. Namely, A is similar to the diagonal matrix with entries 1, 2, and 3 along the diagonal. For a slightly less straightforward example, let's recall the matrix A, whose entries are all 1. We saw that A has two distinct eigenvalues. Lambda 1 is 0, and lambda 2 is 3. And we computed the two eigenspaces. E0 was the span of the two vectors, negative 1, 1, 0, and negative 1, 0, 1, while E3 was the span of the single vector 1, 1, 1. These three vectors will form a basis for R3, as we've already seen. This tells us that A is diagonalizable. We can use these three vectors as the columns for our invertible matrix P. We'll use the two basis vectors from E0 as the first two columns, and we'll use the third basis vector from E3 as the third column. Having made this choice, we arrange from top left to bottom right the eigenvalues of these three vectors from left to right. The first eigenvalue for the first column of P is 0. The second eigenvalue for the second column of P is also 0. And finally, the eigenvalue for the third column of P is 3. This gives us an invertible matrix and a diagonal matrix. And you can check that if you compute P, D, P inverse, then you will get A. Now, as noted in the previous example, the order absolutely matters. If you permute the order in which the eigenvalues appear, then you will get a different matrix that is not A. For example, if you leave P alone, but you rewrite D as the diagonal matrix with 3 in the top left entry and zeros everywhere else, then PDP inverse is the matrix with columns 1, minus 1, 0, minus 2, 2, 0, and 1, minus 1, 0. However, the only way in which the ordering matters is that the eigenvalues match with the eigenvectors. So the choice to put the basis vectors for E0 as the first two columns and the basis vector for E3 as the third column only matters insofar as where we place the eigenvalues. So for example, if we'd made the opposite choice to put E3 in the first column and the two basis vectors for E0 in the second column, then we could use the diagonal matrix with 3 in the top right-hand entry and 0 everywhere else. Finally, for our last example, we want to point out that not all matrices are diagonalizable. So let's take as our example the matrix A with columns -2, 1, 2, 0, -3, 1, and 0, 0, -3. We can see that the matrix A minus lambda I is a lower triangular matrix. So the determinant will be the product of the diagonal entries. So we can see here that the two eigenvalues will be -2 and -3. The eigenvalue -2 has algebraic multiplicity 1. That means that the eigenspace E sub -2 is a line. Since the eigenvalue -3 has algebraic multiplicity 2, we only know that the dimension of the eigenspace E -3 is at most 2. That is, it is either 1 or it is 2. If the dimension of the eigenspace E -3 is equal to 2, then our matrix will be diagonalizable. So we start out by computing the dimension of E -3. To do that, we take the matrix A plus 3i and row reduce. We can see here that the rank of the matrix A plus 3i is 2 because there are 2 pivot positions. Since the null space of A plus 3i is the eigenspace E sub -3, the rank nullity theorem tells us the dimension of E sub -3 is 3 minus the rank of A plus 3i is 3 minus 2 equals 1, which is strictly less than the algebraic multiplicity of the eigenvalue -3. This tells us that there is no basis for R3 consisting of eigenvectors of A. As a result, this matrix is not a diagonalizable matrix. In the next video, we'll see some applications of diagonalizability.